Exam question revision video for GCSE, dice and pie chart. So the question has two parts, A and B, and my thinking is that both parts are about probability, but they're unrelated, so we can look at them separately. So the first part, a fair six-sided dice is thrown twice. What is the probability that a 3 is thrown on both occasions? Well, first of all, a six-sided dice can be assumed to have the numbers 1, 2, 3, 4, 5, 6 on the faces. They could be numbers or they could be dots, but that's the standard dice. And fair means there's an equal chance of getting any of the outcomes. So, since there are 6 outcomes, from one throw of the dice, the probability can be calculated using the probability of the event, whatever it is the number of successful equally likely outcomes over the number of possible equally likely outcomes. So successful over possible. And when we throw a dice twice, we can assume that the outcome of each throw is independent. And that means the throws do not affect each other. And with independent events, we can calculate the final probability by just multiplying the individual probabilities. So, first of all, we'll think about what the probability of getting a 3 is. Well, that means there's one successful equally likely outcome over 6 possible equally likely outcomes. So we get 1 over 6. For the probability of a 3 followed by a 3, because they're independent, we can say that's equal to 1/6 for the first 3 times 1/6 for the second 3. And if we know how to multiply fractions, we'll multiply the tops together to get 1 on the top and 6 times 6 on the bottom, giving us 36. So there's a 1 in 36 chance of getting a 3 from the dice both times we throw it. For part B, we're dealing with a pie chart, as we can see. So our thinking is this, that Llanelli takes up half of the area of the pie chart, and its probability is a half, so the probabilities are the same as the fraction of the area of the pie chart that the town takes up. So Carnarvon takes up a quarter of the area, and we know that because the line dropping down from the diameter is a right angle, so Carnarvon is exactly a quarter of the area, so its probability is a quarter. We can pop that on the chart. And so far we have a half plus a quarter, which is 3/4 of the pie chart taken up. Hence there must be a quarter left. And we're told that Newtown and Abervail have an equal number of committee members, so each of them must have half of that quarter, which is 1/8 of the pie. And we can pop them on the chart as well. So for part 2 of part B, what's the probability that the member chosen as the chairperson works at either the Llanelli or the Abervail office? Well, our thinking here is that from the wording of the question we can assume, in fact we have to assume, that workers work at only one office, or they're based at one office. And this means that working at Llanelli or working at Abervail are mutually exclusive events. This means we can add probabilities. So we have the probability of Llanelli or Abervail is equal to the probability of Llanelli plus the probability of Abervail, and we can write that like that. That green, I've made it green to make it stand out, that is a symbol meaning or. So we have the probability of Llanelli or Abervail equals the probability of Llanelli plus the probability of Abervail. We can get them from our chart, a half plus an eighth. A half is 4/8. You can get that if you don't recognise it straight away by timesing the top and bottom of the fraction by 4. And if we times the top and bottom of a fraction by the same number, it's the same fraction. So we have 4/8 plus 1/8, which is 5/8. Little bit of bonus material in this video, and this is about taking care. Some probability questions involve counting, and it's easy to mess it up. So let's have a look at the question. We've got the Morse code here, and we have to find out the probability of a certain thing happening. And the probability we're finding is taking a random card, so each of these has been put onto a card, and the probability of taking a random card which has exactly 2 dots or which has at least 3 dashes. So that means we need to determine how many of the letters or numerals have 2 dots or 3 or more dashes in their Morse code. Now notice that we need exactly 2 dots or we need 3 or more dashes. Now in mathematics, or means and or. So cards that have exactly 2 dots and 3 or more dashes need to be included, but we must be careful not to count them twice. So any card that has exactly 2 dots and 3 or more dashes, we need to only count them once. And our best bet is to work systematically. So first of all, exactly 2 dots, I'm going to put a little lozenge around each of them, and I think I've got them all. And now cards with 3 dashes, I'm going to put a lozenge around them. And notice there are 2 cards which have 2 dots and 3 dashes or more, but I've only circled them once or lozenged them once. Okay, so now we're in a position to work out the probability. So the probability that the card taken has exactly 2 dots or at least 3 dashes is the number identified divided by the total number, and there are 17 that have got lozenges round or have been identified, and there are 26 letters, 10 digits, and therefore we have 17 over 36 as our probability.